be learning about respiration and the two different effects, the Bohr and the Haldane effect. So we know every tissue, every cell in the tissue has to respire, and these are going to be your respiring cells. And when those cells respire, they're going to use glucose and oxygen, and that's going to create ATP, adenosine triphosphate, which we use for energy, CO2, and some water. Okay, so as a byproduct of respiration, we're going to get a high concentration of CO2 in the respiring cells. And what happens when we have a higher concentration of one mole or ion versus another? Well, it's going to diffuse out, or it's going to diffuse towards a lower concentration gradient. And so now we're going to get some CO2 building up in the bloodstream. And what happens here is, remember, CO2 is a gas, and we can't have this gas in your bloodstream, because think of your blood acting like soda. That's going to be dangerous for you, and you don't want that to happen. So we got to figure out how to get rid of the CO2. So your red blood cell comes driving by all these tissues, and it's filled to the brim with this hemoglobin. And that's the protein binding, those are proteins that bind to oxygen in your red blood cells, and you have thousands of these. And so you can see all the little O2s binded to that hemoglobin. So we're going to talk about the first effect. This CO2 is going to diffuse into the red blood cell because there's a higher concentration in the bloodstream than there is the cell. And this CO2 is going to react with good old water to produce carbonic acid. Took me a second to remember. So this will happen naturally, very slowly, but again, we're building up a lot of this CO2, especially when you're working out. All these muscle tissues or any cells respiring is going to build up a ton of CO2. So we got to figure out the best ways for this red blood cell to grab that CO2 and take it to the lungs, where it's going to trade out the CO2 for oxygen. So we could speed up this process. We could speed up this process with carbonic anhydrase. And this we know is an acid. And what happens when acid's in an aqueous solution? It's going to dissolve into its two ions, H ions and HCO3 ions. Now, because we're producing hydrogen ions, what happens when you have an increase in hydrogen ions? Well, when that happens, we're going to get a decrease. I'm just going to write it over here. We're going to get a decrease in pH because of the increase in H ions. And now this is where the Bohr effect comes into play. Also keep in mind the normal pH for a red blood cell and for most of your body is roughly 7.4. And if we bring it down really low, like 7.1, that's not going to be good for you, and you got to get rid of that. Okay, so with this decrease in pH, we're going to be creating an acidic environment. And now this is where the Bohr effect comes into play. So the Bohr effect states that with higher acidic concentrations, the affinity for hemoglobin to hold oxygen decreases. So what that actually means and looks like is this concentration of H ions is going to come over here and boot off that O2, which is going to diffuse out of the cell, and then it's going to go where the gradient is, or the concentration is lowest, so it's going to diffuse right into the intracellular tissue. Okay, and that's the Bohr effect. Now, what we need to happen, let me grab another color. Okay, so the bicarbonate, oh, you can barely see that. This bicarbonate is gonna leave the red blood cell is gonna actively transport it out of the cell. So it's just gonna boop 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 boop. It's gonna get kicked out. Well, I shouldn't dash it because we're spending energy to get rid of that. So it's gonna leave. And because nature wants to keep charges equal, when we lose a negative charge, we're going to have to replenish that. So actually what's going to happen is the chlorine cells in the bloodstream, which is negatively charged and very present, is going to come right in and take the place of where that bicarbonate was, to keep the charge equal in the cell. And we call this effect the chloride shift. And this is going to happen anytime bicarbonate is present. Okay, now for the Haldane effect. So we got our CO2 over here, right? We got our concentration of CO2. So without going through all these steps, the Haldane effect states that the higher concentration of CO2 present, the more O2 is going to be kicked off of hemoglobin. So this CO2 is going to diffuse into the bloodstream, and then this CO2 is going to diffuse in here, and once it's in here, it's going to be able to come right around and knock off that O2 and do the same thing and bring it right back into the intracellular tissue. And this is the Haldane effect. And just so we're clear, these effects are so effective that pretty much all of these oxygens are going to be knocked out. So you don't even have to worry that all that oxygen is going to be used. And we have thousands of these hemoglobin proteins in the cell. Okay, so this is the Bohr and Haldane effect at the tissue. Next, we're going to do at the lungs or gills, depending on which subject you're studying. Boom, boom. Okay, so now we're at the gills / lungs, where we're going to have this process occur at the lamellae or the alveoli, depending on if you're human or you're a fish. So this red blood cells comes in, and it's just covered in the CO2 and hydrogen ions, and we got the lungs or gills, and it's got a huge concentration of O2. And you know what happens when there's a higher concentration in the gills or lungs? I'm just going to keep saying gills. It's going to diffuse out. And then eventually it's going to diffuse right in here. And actually, once it comes in here, it's actually going to boot that CO2 right off. And it's going to diffuse out and in. I'm not even going to draw it there. And that's how we're able to trade O2 for CO2. But wait, what happens when there's H ions on the hemoglobin? Because remember, this is carrying both. That oxygen can actually come, I don't know, my dashes or lines, and let's say it's coming at it this way. And that's going to boot that H ion right off. How do I go about drawing this? I'm going to use a new color. I'm going to use pink. So that H ion, that positively charged H ion, is just going to be floating around. And our good old friend, remember that bicarbonate we kicked off? Well, that bicarbonate is still around. Our good friend is still around. And what's going to happen is another chloride shift is going to happen in the red blood cell, where chlorine is going to be able to trade with bicarbonate, and this is going to be able to come in right here. So we're trading the chloride shift, we're trading chlorine for bicarbonate again. And here we're going to be able to react hydrogen ions with bicarbonate. Oh man, okay, let's do there. And that's going to give us, remember, because I don't, oh, there we go, carbonic acid, our good old friend carbonic acid. And carbonic acid is going to be able to change into H2O and CO2, and it's going to be sped up with that carbonic anhydrase. And now this CO2 is going to go to the lower concentration and leave the cell. And that is two methods that we're able to knock off hydrogen and carbon, or that's how we're able to get rid of carbon dioxide from the hemoglobin in the red blood cell. And yeah, that whole process is how we're able to trade oxygen, good old oxygen, for CO2. And that's a good thing, okay? Okay, so here's some biochemistry of the hemoglobin. So hemoglobin has it has a bunch of conformations. Where at different points, we're going to have different levels of affinity for oxygen. So here we have the tense state, and here we have the relaxed state. So at the tense state, hemoglobin is going to have very low affinity for oxygen, meaning it's not really going to want it that much. At the relaxed state, it's going to have high affinity for oxygen, so it's going to really want the oxygen. And we're able to get past this first state by changing the pH or the CO2 concentration. And once we go from the 10 state through K1, and we bind one oxygen to one O2 molecule to the hemoglobin, it's going to increase the affinity for oxygen. And we can look at it as, now this one is more likely, this conformation is more likely to accept another oxygen than the previous. And the same pattern follows. So this one is going to be able to accept oxygen better than this state. And this exponential increase in affinity for oxygen is a property of hemoglobin that is essential for us to be able to trade oxygen for CO2 at the tissue or the lungs. Because remember, these red blood cells are flying by super fast speeds, and they have to be able to pick up that O2 or CO2 very quickly, and this property allows them to do that. And you can see here at the 10 state, we're going to be reduced, and then towards the middle, we're partially saturated, and here at the relaxed state, we're fully saturated. It's got an O2 binded to all four sides, and this is the lesson on hemoglobin affinity. And yeah, there's more to respiration, but this is all we're going to cover for this video. Thank you so much for coming to my video, and goodbye.